All right, let's go ahead and get this thing kicked off. How's everyone doing? Having a good build? Yeah. Enthusiasm, I love it. We'll work on that. My name is Mark Sims. I'm a program manager on the Windows Azure Customer Advisory team. We primarily focus on working with customers on deep technical engagements, doing things that we're not entirely sure are actually possible. So I have a lot of interesting days. With me is Simon Davies, TS, focusing on Azure. For those of you who don't know what that is, he sells technical things and also makes them work. And we've worked together on a number of engagements that we'd like to tell you about. So we're going to take an hour of your lives, non-refundable, and go through some of the hands-on lessons we've learned from building fairly large systems on Azure. If design, architecture, scale, availability, and very large things are not terribly interesting for you, I highly recommend many other compelling sessions going on right now. Because if you don't like building big things, this is going to be very boring. And since no one's running for the door, I think we have the right crowd. You think, Simon, we got the right crowd? All right, we'll find out. Okay, there you go. So a couple housekeeping notes throughout. We love questions. We love interactivity. The only thing we ask is that you use the microphones so that we don't have to repeat the question for the recording. And I'm getting a little bit deaf, and he's worse, so the microphones will help us hear you properly. I'm getting there. Okay, so who's run a service in Azure? We definitely have the right crowd. All right, so just going to do a quick recap on agenda. Since we couldn't talk about everything that we've learned about building big systems, we kind of had to pare it down to some of the more, we'll call it the biggest rocks folks tend to trip over or run into at scale. So we're really just going to talk about two key things. The overall scale challenge in terms of how do you take a very large application, shred it up into small bite-sized pieces, and then deploy this in a scale-out fashion on Azure, as well as how to approach distributed caching for distribution and management of application state. So a question I often get asked when I do this is, what do we really mean by large scale? Because large is different for everybody. So every practice or pattern or technique we're going to talk about comes from dropping millions of users onto a live application, hundreds of thousands of ops a second, thousands of cores, and hundreds of databases in data-centric applications. Now, if I'm thinking about a compute-heavy, like an HPC workload, I might go, thousands of cores, amateur, very small. But when we're dealing with state, even partition state, things that are sticky, things that need to be consistent, things we need to understand, it gets a little bit more challenging. So this will be about data-driven applications as opposed to HPC or other kind of compute workloads. Sound like a good-sized number? Kind of boring? Interesting? A few laughs. OK. So has anybody read James Hamilton's seminal Usenix paper on building large-scale internet services? OK. He used to be a technical guy here in Windows Live. Now runs VP engineering for Amazon. Really smart guy. Put together a paper about 5 years ago basically saying, this is everything we learned about running Windows Live. And I always go back and think about this paper going, it's 5 years old, and every single thing in here is true. And it doesn't change. A large number of the things in there about actually managing a large service at scale, we actually handle in the Azure platform. You get single system image. You get role management, not server management. You get geo-distribution. You get configuration and code as a unit. You get service level recovery. These things just happen for you. So we don't have to spend a lot of time talking about them because they're just there. So because we took care of a number of these problems in Azure, that just means we get other things we get to focus on. And this will be the content of both part 1 right now and part 2 about 45 minutes after we go through this session. And we'll be available in between and afterwards to answer questions that we don't get a chance to get to in the session itself. So part 1, we're only going to talk about 2 things because they're a little involved and they have many different permutations. It can be a little tricky depending on your workload. So we're going to talk about service partitioning, primarily about data partitioning and state management. Because stateless stuff is low state is relatively easy because my load balancers handle it. I add more relatively stateless web servers and app servers. Pretty straightforward. We know how to do that. When it comes to managing coherent, durable state, that gets a little trickier. So we're going to spend a lot of time talking about that. This will primarily be in the context of relational data management because that's also tends to be fairly hard to partition. And when you're in a lift and shift world, when you have an existing application and you want to bring it into a service world, whether you're an ISV with a packaged software product or you have an in-house application that you want to bring into the cloud, these are the things that tend to have been specifically built with a globally coherent state, a scale-up model in mind, and you have to pivot them in order for them to play nicely with Azure, to work with the distributed fabric rather than work against it. The other piece we're going to talk about is optimizing for density. So in a box world where I capitalize my hardware assets, there's always a bit of headroom. I always buy a little bit more than I need because, hey, I might be successful. It's kind of a cool thing. But one of the results of that is some of the programming practices and techniques we do, some of the optimizations, they just get lost in the background noise because the server's big enough. If I'm running 10 or 20% less efficient than I should be, it didn't matter because I had to buy a bigger scale unit. I had to buy a bigger box. When I'm working in an elastic environment, the efficiency of my code balanced against developer agility is cost of goods. So some very small optimizations can actually have a profound impact on your bill. And we like to keep the bills low and developer agility high. It's good, right? Any CFOs in the room? Probably not. I know, not as nerdy, but still important. The second session will focus around how do you design for availability in an occasionally unreliable substrate. Azure, like all really large-scale cloud infrastructures, is built on a lot of moving parts on commodity hardware. If we went out and bought fully redundant hardware for every single piece in Azure, we could do that. The amount of money we'd have to charge you in order to run that would be it just wouldn't work. So instead of thinking about how do I harden my infrastructure in order to make everything work and keep the lights on, which is what we've been doing quite well for about 20 years, probably a little longer, we instead need to think that the underlying fabric in which we run things is going to run into occasional failures, and how do we have software that just goes, whatever, I'm just going to keep working. And we're also going to talk about the importance of designing for operations. This is probably the single biggest shift in mindset, moving from a box product where someone else is responsible for managing it to a service where you're responsible for managing it. In fact, we, as Microsoft, this is something we've gone through as a cultural shift in terms of understanding once the CD went out the door, well, have fun with that, versus no, we are now your IT department. We need to make sure that we know we have the right insight and you have the right insight into what's going on. So we'll spend a lot of time talking about that in the second session. The reason this is done as a two-parter is these are two sides of the same coin. It's extremely difficult to separate the design considerations for scale and the design considerations for availability. They're very tightly related. So, who's heard of Harry Potter? I know it's a bit of an unusual segue, but we'll start there. Oh, come on, people. There we go. That's better. It's where you're all on, playing with your new Windows 8 devices. Yeah, I didn't get one yet. I don't get mine until later. Okay, so Harry Potter Online was a project by Joe Rowling who wanted to extend the Harry Potter universe and the experience into the digital world. And back in, was it May? June. It all blended together. In partnership with us and the Pottermore agency, we brought the Pottermore.com website online in Azure. And it's a really interesting website from a number of perspectives, in that it's personalized, it has durable content and exploration and a social experience in terms of friends, comments, likes, and also has interactive gaming. So these all sound really cool, but from the perspective of running a very large-scale service, these are all highly stateful operations. It can be quite challenging to run when, in your first week, you get the pleasure of 1 billion page views, tens of millions of users, 100 millions of daily impressions showing up, and you've got 1,000 cores and 500 databases out in Azure first week. So this was a really exciting launch. We had a lot of fun, learned a lot of really great stuff, and we're going to share not the exact story here, but more of a composition of several customers just like this. The reason we're bringing up this one we have a public case study, and we can't talk about some of the details of the other customers. So instead, we're going to pull back a little bit and think about the application from a workload perspective, and specifically thinking about the degree of state and the management of state in the application. Because this is really what you need to focus on when we think about scale, because these are the seams that start to appear in your application. And this list goes from easier to harder in terms of state management. So let's think about content delivery. This is your average website experience. I have content, it's delivered to everybody on the site, usually with an authentication check. I have a limited amount of state on a per-user basis. I have a shopping cart that shows up and may go away. I have a login, I have some preferences, but the amount of content that I need to manage on a per-user basis, on an isolated basis, is relatively low. That one's pretty easy. Now we move to content exploration. This is where I have a highly personalized experience on a per-user basis, but doesn't touch any other users. This is I remember my order history. This is I explore through the Harry Potter books. This is any form where The system needs to remember me, what I've done, and what I like. Okay, but again, very isolated, because if all you can remember is user by user, your system will still scale because you don't have relationships between data. And now things get interesting. Social graphs and content. 10 years ago, even 5 years ago, the ability to understand relationships between your users, almost science fiction. These days, it's becoming to be table stakes in terms of not only creating an ecosystem, but understanding relationships. So if I think about social graphs, they have this really interesting property. It's a per-user comment, but I also have global reach. I can reach out to any other user in the system. And this has pretty profound implications when it comes to the ability not just to partition to a single data center or a single region, but when I go with global distribution, this becomes a very serious problem, because photons and electrons have mass and they move slowly if you have a very large number of them. At this scale, a lot of these challenges, they just come down to physics. And we can bend the rules, but breaking them, well, I'd have a Nobel Prize if I figured that out. Okay, but the other interesting part about a social graph is it's a loosely consistent experience. If I go and I post a comment on my friend's feed, as long as I see it immediately, that's okay. If my friend doesn't see it for a second or 5 seconds or whatever your SLA for a business experience is, that's fine. So we can play some games with the consistency. And then finally, to one of the harder problems, which is interactive gaming. So this shows up in many different forms. It can be chat, online poker. I don't play it, but I understand it's pretty popular. Has this challenge where you have interactivity. The Pottermore experience has wizard duels. So you have this, I need to bring n players together that have a relatively coupled, cohesive view of state. And if they happen to be living in 2 different parts of the world, this can get a little challenging. So these are the kind of problems we're going to talk about in terms of how you approach scalability. Sound interesting? A few nods. I apologize if I can't actually see too much. The lights are very bright. All right, so let's think about scaling. It's really kind of 3 things we need to think about. We need to think about adding capacity. This is the standard way of, all right, I'm going to go in, I have X units, I need twice as much capacity, I'll add twice as much stuff. As long as you have a way to linearly add capacity, this works pretty well. And depending on the kinds of things you're doing, that's one of the ways to get to scale. But it's not the only axis. We have 2 others we need to think about. Because when we're running a service, cost of goods and efficiency of delivery is very important. If I have an unlimited checkbook, and if anybody who has one of that, I'd love to work on a project with you, but most folks don't. So if I think about optimization, this is the normal things we think about. Optimizing my SQL queries, optimizing my code paths, running profilers, looking at overall end-to-end kind of component-by-component performance. This is pretty straightforward. We know how to do this pretty well. I'm not going to spend a lot of time talking about that. But it's a really interesting one when I start thinking about different ways to manage state and different ways to manage data. So who here runs a SQL Server in a box form on premise? Okay. How much effort is involved in creating, managing, running, maintaining, upgrading, scaling a box SQL Server with full reliability, failover mirroring, always on? The fact that this list is getting long, this starts to sound pretty impressive. And once you've created one of these things, you tend to want to put a lot of stuff in it. And this is good. We have a great product in SQL Server. But what it's led to is if we put so much time and energy into creating a manageability experience around having SQL available and always there, the inclination is to put everything in there because it works. I'm going to take my blobs. I'm going to take all my data and put it in SQL because it's there, it's reliable, it's secure, it's safe, and I know how it works. Going to the cloud, to a world of service composition, this equation changes a little bit. If all of a sudden the cost of standing up a file management service is 1 API call, and the cost of standing up a SQL service is 1 API call, polyglot data management, the ability to aggregate and compose multiple types of services, suddenly becomes very attractive, not just from a cost perspective, but from a developer agility and code complexity perspective. So we start to see the relational data store is a great place to put relational data. Everyone knows what I'm talking about when I say relational, right? Set-based, relationships between things, querying, aggregation, all that good stuff. But especially when we think about web applications, not all data is inherently relational. There's a lot of key value data, there's a lot of key column data, and there's a lot of blob data. So just saying, hey, we're going to put everything in one store because that's simpler, has some downsides. It's usually true on premise, but when I move into a service composition, I may go, it's okay to play to the strengths of each of the services that I have available. It's okay to hold my non-durable, loosely consistent data in distributed cache because its pure memory is 100 times denser than SQL, but it's not queryable. So I'll make these trades. And we'll show some examples of that. So one thing I talked about was adding capacity. So let's think about what adding capacity is in terms of managing scale units. When I think about this on premise, it's okay, how big a server do I need to buy to put my globally coherent state on? I'm going to go give one of our great hardware partners oodles of money, rack some hardware, plug in some cooling, and plug in some electricity, and everything's fine. Azure's a little different. It's built around scale-out units that you can add. There's more services, there's more scale units than these. I'll just talk about a couple of them, the common ones that pretty much most of the services we see baseline on. Azure Compute, whether I'm running web roles or worker roles or new durable VMs, they come in a variety of sizes. If my workload doesn't fit into one, and generally real workloads don't fit into one, I need more of these things. So I pick the appropriate size, and I get enough of them to fulfill my capacity. If I need more capacity, I add more. If I need less, I dial it down. Pretty straightforward. Azure Storage, the durable store for data, whether you're working with blobs or queues or tables. Each storage account, I get 100 terabytes. It's pretty good. But that's not usually where you end up having to scale. And we have one person that didn't think this was really good. That's actually really good. You guys are a great audience. So normally, I will not hit 100 terabyte limit first. Normally, I will actually hit my throughput limit. I will hit the operations limit. So an operation would be writing a chunk of a blob, inserting or deleting a message, or posting or reading or writing from table store. So that's actually my cap. And within each of these, as like an individual partition in table storage, I can do 500 operations a second. So within there, if I want more, I need to use more partitions, or at some point, I need to use more storage accounts. We can talk about some techniques for doing that. But again, this pattern continues. Now, no doubt, in the future, we'll have different sizes of scale units. The slope of the curve will change, but the shape of it won't. You're always adding relatively small scale units compared to what we can buy on premise. That's what gives elasticity and the ability to match supply with demand, or capacity. And finally, something we'll spend a little bit of time talking about is Azure SQL Database. If I say what it used to be called, someone from marketing will probably come in and throw things at me. And I'd like to avoid that, at least for the first session. OK, so we have a maximum size of 150 gig. And everyone goes, well, I have a terabyte of data. I just need like 8 of these. Again, that is the static, the relatively slow-moving metric. The more important one is, what's the live metric? How many queries, how many operations, and how expensive are they? And this is where most folks tend to trip up. I have, unfortunately, been involved in a number of engagements where we have very large systems and one poor little abused SQL Azure database going, help me. So let's talk about how we actually take that and split it up. But really, this is, when I think about partitioning, I need to partition and scale out all aspects. Low state aspects are easy. In a web role and worker role, the load balancer handles these things mostly for me. It'll basically give me round-robin assignment on incoming connections. However, my relational data, and to a lesser extent things like tables and blobs, is relatively high state, and I need to think about how I partition it. And one of the reasons that SQL in particular tends to be very challenging to partition is because the SQL language, whether it's Postgres or Oracle or SQL Server, has this notion that all data has roughly the same cost to reach as any other piece of data. This concept of physically partitioned data is not in the semantic of the language. There's nothing I can... anyone ever used Hadoop, written a MapReduce query? A couple of hands. So when you're working with big data and doing MapReduce queries, the concept that this is a physically distributed system is baked into the query semantic. If you write a mapper and a reducer, what you're saying is this piece can run on a different machine than this piece, and I expect it to, so it won't let me do things like cross-network Cartesian joins, which, for those who aren't familiar with a Cartesian join, it's really expensive. OK, so ultimately, if I have a large system, and it's based on SQL, and I have a lot of relational data, and I want more throughput or more capacity, but mostly throughput, I need to add more databases. OK, well, adding more databases is pretty easy. But then how does my application connect with the right set of data in the right place at the right time? Let's go through some techniques. So this is pretty baseline stuff. I'll tie it all back to something a little bit more sophisticated in terms of real-world application in a second. Just want to make sure we have the baseline concepts down. Because we I actually don't tend to talk about this a lot in the database world because you don't have to do it very often. Usually the response is, give me a bigger check, I'll buy a bigger machine. Okay, so horizontal partitioning is pretty straightforward. I take my data set, I slice it based on some key, and I put them in different physical stores. And then I route my application to it. Who sees the problem with the algorithm displayed on the screen here? Exactly. This is an unbalanced partitioning strategy. In general, and I'm just speaking for North America here, last names tend to cluster around certain letters. So if I basically say I'm going to split my data set into 26 even areas, I will have some very hot areas and some very cold areas. So I won't have enough capacity in some places, and I'll be wasting capacity in others. So we're already starting to dig into, this is not an easy problem. I alluded earlier to polyglot approaches, and we see this both within a relational store as well as polyglot, where I have different types of data. Now, I'll either have different types of data in different tables, or I'll have different types of data in different stores. Very common example, if I have blob data, binary data that I don't manipulate it, I take it, I put it there, and I access it. Photos, thumbnails, very common. Putting that in a relational store, it basically says, I'm taking a very rich engine, and I'm parking a byte array there. Well, we have new ways to park byte arrays. Don't get me wrong, parking byte arrays is very important. But I shouldn't use my most sophisticated, expensive store to do that. So, pretty simple example. I'm peeling off some of these other kinds of data and putting them in an alternate store. And since the cost of managing blobs and tables is essentially zero because we do that for you, this starts to become very interesting. Most commonly what we see is a mix of these approaches. Peel off data into the appropriate stores, slice up the relational data, or actually these other ones will be partitioned as well, horizontally. So this begs the question, what process do I actually need to go through in order to understand and map partitioning to my application? Because it's not magical. So regardless of the actual implementation, something will go through all four of these steps. If you work with table storage, steps 3 and 4 are done for you underneath the covers. If you work with a load balancer, these are all done for you based on a load balancer policy. But somebody had to implement this logic. So again, generally 4 steps. I'm going to select my partition key. For my previous example, that was the last name. I want to extract a partition value that's smaller to work with. So oftentimes this is done with a hash function, which we'll discuss next. Or it's something as simple as I'm just going to grab the first letter of the last name. Yeah, I think we saw where that went. I'm then going to map that partition value to some logical assignment, not a physical one, just a logical bucket, and then that'll finally go down to a physical resource. So last name, grab the substring, have a map that goes from there to my logical, and then from my logical to a connection string. So a common technique that we've seen at some of the larger social providers is a range-based partitioning mechanism. A little more sophisticated. This does have some problems, and we're working on kind of some better, more sophisticated ways of handling this. This one basically, I start with my partitioning key. I mentioned earlier that all these workloads are very user-centric. So the user identifier, whether you use a username, an email, or a GUID that's assigned when you register, it's a very natural way of carving these things up. I tend to prefer the GUID as the identifier because it lets you change the username of the email without rippling through your system and causing a massive rebalancing activity. So when I get this, I'm going to take this, but this is not something that really lends itself to slicing into ranges or into buckets. I'm going to convert it into an integer value first. So luckily we have these nice little functions, non-cryptographic hashing functions. Anyone know why I would want to use a non-cryptographic function? As opposed Speed, absolutely. Speed and performance is a big one. No, it's still one way. Remember earlier we talked about distribution? So think about what a cryptographic hash does. It says that I'm not going to give you collisions except in very specific circumstances, and that's what it's based on. Your signature is going to be unique. If I actually want to distribute things, I want collisions, but I want evenly distributed collisions. So we have different kinds of hashing functions depending on what we wanted. If we used a cryptographic hash to do partitioning, well, one, it would take forever because it's doing a lot more math, and all my petitions would have like one item in them, and that would be suboptimal. If you wanted to actually build a database system like that, we would sell you that many databases. And then we would probably come by afterwards and going, you know, you have 100 million users and you wanted 100 million databases. We could probably recommend some better ways of doing that. So finally then, I map this range down to a logical shard. So in the code sample that I'll bring up if you guys are interested, I basically take my entire range from minus 2 billion and change to plus 2 billion and change, and slice it up into 5 or 6 slices, have a simple little function that basically says find which shard this maps into, and then give me an object that has a connection string. You guys want to see some code? All right, let's see some code. All right. There we go. So let's actually go through and actually see this stuff running. Just as a FYI, we'll cover this at the end. Every bit of code I'm going to cover here today is actually part of a code sample that we're going to be publishing on CodePlex towards the end of the year. We're just going through basically cleaning it up, doing the usual LCA stuff, making sure there's good documentation. So anything you see, you'll be able to get your hands on fairly soon. So let's just go through some basics. We're going to start with a username. We're going to do an invariant. If I actually wanted this to be case sensitive, I wouldn't bother, but I tend to fat finger stuff, so as long as it's unique to an invariant state, doesn't seem too bad. So I'm using a little hash function called murmur3. It's basically we did an implementation based off the algorithm described in Wikipedia. It's a very fast, evenly colliding hash. Basically, we went and tested this out over 100 million usernames, and I think we got about a 98, 99% flat distribution. So it's really nice. And the more things you throw in there, the more it flattens out. But this is just one. There's probably a half dozen different ones that are all comparable. And pick one you like and work with it. You just realize once you've picked it, you're pretty much stuck with it. OK, so we go and we get a nice little hash value. I got that minus 7 million and change. It's probably not showing up too well at the back there. So let me bring up my little watch window and boom, boom. Zoom, it works. Fantastic. So minus 7 million and change. All right, so then we go through. I've just got a little shard mapping thing here. This basically just loads the static set of shards from an XML file. You have two options. You can have another dynamic data store, like a table or a blob or SQL, that holds your map, or you can roll it out with your application code. It's basically an agility versus determinism choice. No right way, just depends on how you want to write your app. So I'm basically just going to up-level this shard key, because the range-based partitioning we happen to implement works with integers and byte arrays and GUIDs and other things. So that's just more of an abstraction layer. So then I'm basically just going to say, hey, tell me give me a shard where this happens to be in range. Hey, I've got a shard. It basically maps between minus 12 something lots and minus 4 something lots, where my minus 7 something in lots happens to fit. So then I'm just going to come down. I'm going to pull out my connection string from there. Yep, there we go. And you saw my database name. Oh my God. OK, and then I just crank open the connection and I work from there. So again, works. It's a little bit of extra stuff. In a production code, you wouldn't be using this stuff directly. You'd have some form of data access layer that was actually masking all of this from your user code, as well as handling things we'll talk about in the next session, like retry logic, logging, transient fault handling, all that good stuff. And come on, mouse. There we go. Hey, look. Oh, I already did that demo. We can move on to the next slide. So I talked a little bit about the various partitioning algorithms. There are more. These are 3 of the common ones that we see. So range-based, I basically take the range of possible values. I chunk it up. They do not have to be evenly spaced. I can have wide ranges and small ranges to account for hot spots and cold spots in my system. And the rebalancing, basically repartitioning, would involve splits and merges on these ranges. So if I have relatively small ranges, I have relatively cheap splits and merge. The challenge you run into, again, comes back to this distribution concept. And this is something that's very particular to social graphs. Does anybody know what a ZIF distribution is? OK, so let's talk about kind of 2 key concepts, or 2 key types of social graphs. I have the Pottermore, or kind of Facebook-esque graph, where I have a number of friends. And everyone has relatively the same order of magnitude of friends. You might have 5, you might have 500, you might have 5,000, but you generally don't have 5 million, unless you're a very, very friendly person. Then I think about something like Twitter, where we have 2 classes of users. I have ordinary users like me, who has 100 friends, or followers, as it were. And then I think about the celebrities of the world, who have tens and tens of millions of users. These are foundationally different. If I take a range-based approach to managing a celebrity, I'm going to have this very narrow range of 1. And if I have more than one celebrity, I start to create a lot of fragmentation in the system. This ends up being very bad. So what a lot of these things do is there's an inflection point at which the system goes, you, sir, are a celebrity, or ma'am, as the case may be. We're going to pick you up out of this system and drop you down in a different one. Or if you've paid us enough money, we'll put you there from the beginning. So you start to get into a more sophisticated partitioning algorithm that can actually identify you and which back-end system you route to. Logical bucketing is basically, I'm going to take my entire range, I'm going to split it up into a large number of buckets, 16, 30,000, and then collect buckets onto a physical resource. One database server might have a dozen buckets, one might have 3. Then rebalancing is picking a bucket up and moving it to a different physical resource. And finally, there's lookup assignment based, where basically I maintain a lookup table for every single item, for every single entity in my system, and then I can route directly. Now, lookup is challenging because then I have to maintain this giant consistent table. If I have 100 million users, I need 100 million items in a hash table or some other equivalent lookup format. So normally what we'll see is, and lookup tables are usually based on, are actually usually implemented using a logical bucketing system to handle the root nodes. 2 more. I promise not to drive everyone out. OK, just a quick map recap, range-based. Start with John Smith. I hash. I get a value. I didn't update that because that's actually my hash value. I bring it into a shard map. I go down to resource map. I end up with a database. Pretty straightforward. Logical bucketing-based. Again, same workflow, different functions. So if I have generic interfaces, they actually just kind of plug in here. So in a case where I have a shard map with 32 buckets, I basically mod 32, my hash value, and then do a math.absolute so I don't end up with negative bucket numbers. Map it into a resource, and then the resources overlay on top of physical databases. So a SQL Azure database is a relatively cheap container to use because you can just create one and you get a certain physical resource allocation. We've got customers that actually use this as their isolation mechanism with 15, 20,000 databases. Because a database in the SQL Azure world, oh, sorry, I'm not allowed to say that. Marketing will come charging in. The Windows Azure SQL database world is a very cheap entity. It has virtually no management cost. So if I use my database as my physical container with a one-to-one mapping, I don't need to do anything fancy with my schema management. If I try and coalesce multiple logical buckets into a single physical database, I either have to use different schema or different table names. That gets a little more complicated. And finally, there's lookup-based, which, again, the only difference is this is now a very stateful partition management system where I take that value, I go to a lookup table, I come back with something, and then that routes me to the appropriate shard. So I've implemented all 3 of these with customers with more than 20 million users. And they just have various forms of complexity. It's the trade-off versus complexity versus performance versus distribution. And we'll be releasing sample code to demonstrate all these techniques. All right. So we're going to switch over and go a little bit about caching. We promise we won't bite if you ask questions. The mics are just standing there, a little lonely. Sure.
So is the idea of creating shards so that you never have to cross-shard?
So the question in the back was, if we create multiple shards, is the intent to avoid cross-shard queries? Or actually, more point, scatter-gather queries. Let me handle those 2 separately. So if I needed to answer a question based on data that's been sourced from 2 different places, there's generally 2 patterns. One is I need to get the data from A and the data from B, bring it together, and then answer a question. Who's worked with distributed transactions? MSDTC? Did anybody enjoy that experience? I'm going to go on record and say that distributed transactions are a symptom, not a cure. Trying to maintain that degree of tight consistency in a highly distributed system has a hard barrier of physics. If you're willing to dial down your throughput knob to a certain extent, you can support this. We don't have it in the platform right now, but again, based on our track record, it wouldn't be inconceivable that we'd support distributed transactions to some degree. But it's hard physics. Who's familiar with the cap theory? Brewer's theorem? OK, a couple folks. Basically, it says that you get an iron triangle between consistency, availability, and performance. It's not exactly how it works, but it's the easiest explanation for now. And that if you want a lot of availability and a lot of performance, you kind of got to give up on consistency. Because it's just physically challenging to get all these distributed systems where time is very slippery to agree. Even in a distributed system, it's difficult to even get machines to agree on what time it is, let alone the specific value of an item. So if I need to be able to, so distributed transactions are out for the time being. So coming back to those two types of workloads. One is I want a global visibility. I want to ask a question about all of my individual partitions and then come up with a composite answer. A leaderboard, statistics, metrics. These are common examples of this scatter-gather activity. If I need to be able to get information from two different points, the general approach you have right now, and if you come to SQL Pass, we'll tell you more about where we're going, is I generally will bring both of these pieces back to a common point, usually in my application tier, do my data manipulation, and then push it out. The normal way that we'll handle the eventually consistent update when I'm here and my friends are over here is I will write my update immediately, and then I will create a background task either through TPL or throwing a message out onto an Azure queue with a worker process that then goes in behind the scenes and does the update. Trying to manage tight consistency between two partitions, very challenging to do at anything other than kind of very low throughput. Did I answer a completely different question or the one you had in mind? Okay, so the exactly. If you need to, so just to recap that for the purposes of the recording and posterity, if you need to be able to ask a question about that depends on two pieces of data, the state of the platform right now is generally that you're going to ask each question individually and then compose it in an application tier. If you have a data model that has a non-trivial percentage of these types of applications, you probably either A, have an application that's very amenable to scale up, like a data warehouse, or you're asking the question the wrong way. Now again, there's a large number of questions that you're going to be forced to do this sort of thing. They're hard to scale out. They're not always a great fit for cloud. Actually, I didn't cover that at the beginning. There are workloads that do not work in a scale-out, commodity hardware, elastic environment. Banking, finance, things that require microsecond level determinism. This platform is very good at certain types of workloads, just like other platforms are very good at other kinds of workloads. Sometimes, if you feel that you're just kind of bouncing off a wall time and time again, you're probably trying to hammer in a nail with a screwdriver.
Just a quick question. When you talk about sharding, why did you skip talking about federation?
So, that's an excellent question. I was actually just waiting. Someone was going to answer it. So we have a technique or a feature in SQL Azure. I did it again. Someone, throw something at me if I do that again. Called SQL Azure Federations. So let me just go back a couple of slides, and I'll talk about what it does. So remember our four things that we have to do? SQL Azure Federations does the last three for you. Basically, it provides a monolithic, self-contained capability to do a certain pattern of scale-out. Let me repeat that part. It provides an easier way to implement a specific class of database scale-out. It masks the connections for you. It handles connection affinity. It handles logical assignment. And it does one of the two rebalancing activities for range-based partitioning. It handles live splits and offline merges. It's a great technology, but it doesn't solve every class of problem. I talked a little bit about where range-based partitioning falls down. If you have an unbalanced social graph, you're going to end up in a lot of trouble pretty quickly with a very fragmented range set. And also, because of the way that it's built, Federations does very interesting things. It hides a lot of stuff for you. But at some point, you hit the issue with every purpose-built monolithic entity in that you go outside of its design boundary. If you try and put 1,000 shards in Federations, everyone's going to be crowded up on the central choke point, which is the gateway. The cost of hiding this from you, of hiding this logical to physical mapping inside the protocol, is that everything travels through the same choke point. In any distributed system at enough scale, any shared component will bottleneck. And that's what happens in Federations. It's great. It's not that it's a bad technology. Everything has a design limit. And in a lot of these that we've worked with, it was a combination of we couldn't use range-based partitioning because of the distribution mechanism of the data, and we were working with so many databases that we were just basically hitting choke points on the way that it was implemented. We see this time and time again when you have this wrapped system that provides a turnkey experience. There's always a trade-off. What we ended up doing was more sophisticated. We had to do a lot more work that Federations would have done for us, but we were working at scale points and distribution points outside of its design boundaries. Yep, sure.
You mentioned your sharding databases.
Hmm?
You're reducing load on individual database. What problem we see? We don't have published numbers on scalability of individual database.
Okay.
How many requests per second you can survive?
Excellent question. I was waiting for this one to come up. The question was, we haven't published numbers on the basically individual capabilities of a SQL Azure database, so it's difficult to design for. So there's two pieces of this question. One is, in its current form, come to the SQL Pass if you want to hear more, SQL Azure is a multi-tenant shared database. Who drives to work? Who has a private road between their house and their office? What happens at 8 o'clock in the morning? Rush hour. What happens at 2:30 in the morning? Road's pretty empty, right? A public highway or public road is a multi-tenant system. It's relatively cheap to offer a large range of services to a broad number of customers. But if everybody wants to use it at the same time, performance is degraded. SQL Azure is the same thing. It is a multi-tenant service. We have options coming to reserve allocated capacity. They'll be more expensive because we're not sharing anymore. So from that perspective, deterministic numbers in a multi-tenant environment, it doesn't work from a physics perspective. The other thing is, I can talk and I can say that you will get 500 operations per second out of a single Azure table partition, because every recall into a table store has roughly the same cost as any other call. The difference between select one and select star from a table is nearly infinite. So the only real way you're going to have to test, you're going to have to take your workload and put it in production. And if you, and we can chat afterwards when I'm off the mic and I can share a little bit more detail. And you're all welcome to hear this part. Is that if you have an application that requires fairly predictable performance, we have some new options coming.
And when you mentioned public highway, I sharded to 300 databases. How can you ensure that you're not sharing same hardware resource and not fight with each other?
So the question is, if I shard out to 300 databases, how do I ensure I'm not sharing? So here's the interesting part of the physics. The more databases you have, the more failure points you have, the more likely you are to experience failure, and the more likely you are to be crowded out by someone else. But the flip side is, it'll affect a smaller piece of your system. It's just physics. If you have an application that cannot survive and cannot sustain non-deterministic performance, you have to go with reserved resources. We'll have options for that soon. But there really is, it's statistics at some point because it's relatively shared. I'll be honest, that isolation model is something we're not used to. We don't have a lot of, as an industry, it's not something we're terribly good at developing against. We got the first hit of that back in like the early 2000s when we first started moving to virtualization without directly assigned disk channels. And all of a sudden you're going, why? It was my latency going completely variable because we're sharing things. We're now in the second or third generation of that. And we're evolving the capabilities to say, some of my apps, some of my workloads, some of my features, it's okay if they are a little bit unpredictable. These other ones, I need these, I'll pay more because it's worth more to have predictable performance. Sorry, this question in the back was first?
So what's the story then to adjust the number of shards dynamically? Because we're talking about elastic scale, but this is still pretty static. These are cool, but it's a really complex problem to kind of merge it again into that chart or to have more charts. You read this through because it's also cost.
Yep.
So do you have a story for that already?
So the question is around basically saying, this is really hard. You're going to make it easier? Would that be a fair paraphrasing? Okay. So right now, this is me being extremely candid. Hard things are hard. We know they're hard. We know we need to make them easier. So there's some stuff on the roadmap. Unfortunately, I can't talk about it, but we realize we do not want to put everyone through this. We want to bring the point at which the platform makes things accessible and easy much higher up. There will always be an inflection point where you have to start getting custom. That's never going to change. What we want to do is lift it further and further up that point. So if you ask me this question in the near future, I will be able to tell you a lot more about how we're going to do that. But all I can say at this point is we realize this is a really serious problem, and we need to make elastic scale of highly stateful aspects of the systems a lot easier to manage. I know, complete marketing answer. Unfortunately, that's all I'm allowed to say. In front?
This is related to his question. In general, multiple databases under the same subscription are attempted to be allocated on different machines, right?
So the question was, inside a single subscription, will we attempt to allocate different databases to different machines? Yes, but since this is the building big, we're going to peel back the covers a little bit, and I'll talk about some of the interesting things that happen at scale. So actually, let me park that question. We'll be here for the second session. Haven't driven you out yet. There's some part of that question actually has to do with how SQL Azure implements high availability and failover. So when we talk about that, it'll probably be a lot easier for me to cover that there. And I actually do want to spend a little bit of time talking about distributed cache. We will be here in the interim, so if we want to park the SQL questions or the data-specific questions, we will get back to those. Sorry, Simon, I haven't let you talk yet. This happens a lot.
I sort of predicted this was going to happen to our colleague who was stood here before. But Mark was going to talk a lot, so hopefully it's useful stuff. So let's think about distributed caching. You've got more capacity, and we just touched on a few of the issues that this brings. It's not practical to query that durable store for every request, for some of the reasons that we talked about. You know, fanning out a query across 500 databases is not something you want to do while the user's waiting. You want to optimize your system for cost. You don't necessarily want to bear the cost of going to that store. Some stores cost money to touch. Windows Azure storage, we charge you for I/O transactions. And of course, as we said, not all data needs to be immediately consistent. Now, one thing that's a common implementation across all these systems is using a distributed cache. And one of the things that's most apparent here is that there's a different query semantic. You've got a key-value pair, essentially. You have a key in a byte array. So you can't do the same sorts of queries to the cache that you can do to the database, yet you need to get the aggregation of data done there. It's not durable state. Typically, these things are keeping data in memory, and that's a good thing because it gives you very quick responses. And it's built for a scale-out architecture. Basically, there's a bunch of servers and a bunch of clients. The clients know about the servers, and it scales very nicely. And the examples that we've worked with have been Memcached and Windows Azure caching. So the Windows Azure dedicated cache, for those of you who know, we have a service. We're talking about the Windows Azure dedicated cache. One of our customers, there was a large sporting event took place in London during the summer. And one of our customers was actually the Press Association, who are or were the host data and press organization for that event. Besides doing the normal things that a press agency do, producing photos and journalism and those sorts of things, they do a lot of work in the sports data space. They produced some services for their customers globally to basically publish data about what was happening at the Olympics. Some of that was very real-time data. The 100 meters takes 10 seconds. Some of it was much more long-lived data, what the current state of medal tables were or what the historical state of medal tables might be. This app was, just to give you a little bit of a flavor of the implementation, it was a Node.js app hosted in IIS using IIS Node, deployed across 8 data centers. And you can see some of the figures there. On the busiest day, 2 billion requests, and peaked out around about 50,000 requests per second. So a pretty large application. One of the interesting contrasts between that application and Pottermore, when we did Pottermore, we sort of knew roughly that we got a big problem, but we had some sense of what the size of that was. There was some data about the pent-up demand. This was very different. The only data points we had were that every previous Olympics on the internet had been bigger than the last one, and the statistic the development director gave me there was that every Olympics had been the busiest day. The first day of each Olympics was the busiest day the internet had ever had. So the design points for this system were actually much, much bigger than the numbers that turned up. Orders of magnitude bigger. We could have gone way bigger than this. Now, that application is a representation of a pattern really about caching resource data, about pulling data from some back-end system, publishing it into a cache, and then having that data served out of the cache. And again, if we go back to the question about fan-out queries, one way of thinking about that is that you can do some of those queries, not all of those queries, but you can do some of those queries and create the data by doing these fan-outs in the background. And one technique for doing that is to have a worker role instance that does it. Now, there's a problem with this diagram. Anyone can spot it. So the problem is there is a single worker role instance depicted on here. And of course, we know that Azure is not providing us any guarantees about the availability of any single instance. So the question is, what happens? How do you make this reliable? Of course, the easy answer is you create 2 of them or more of them. But that introduces another problem. Now I need to have a mechanism for those things to coordinate the work, and suddenly life gets much more complicated. A couple of techniques we've seen used for that problem. You can actually use SQL as a queue. It has a nice little lock hint called read past, which enables competing threads to hit the top of a table and pull off items at the top of that table without getting in each other's way. So that technique's fairly successful for this sort of application. Another way you could do it if you wanted to go for an active-passive model is you could take a lease out on a blob in the blob store. The guy who has the lease is the active one. The other guy's constantly trying to get a lease on the blob. If he gets the lease on the blob because the other guy's gone away, then he becomes the active one and he takes over. But generally speaking, this is a really quite a simple thing to implement. You're basically pulling and aggregating data from some back-end service. And in the PA's example, their back-end data service wasn't even in Azure. It was outside. They were just surfacing the data and using Azure effectively as a high-scale publishing mechanism. So when we think about those 2 technologies, Memcached and the Windows Azure cache, we need to think about some of the qualities of those things and how they map onto Windows Azure. So we think about Memcached. One of the things you have to think about to use Memcached is what's the deployment model? You have to choose a Memcached implementation, test it, make sure it scales on Windows Azure, wrap it up in some code, deploy it in your package, fire up the process, monitor the process, make sure it still runs, restart it if it falls over. You have to think about how to surface performance data out of there. One of the interesting problems is that Memcached uses client-driven hashing algorithms. In other words, the client knows about all the servers that exist, and it uses that knowledge to determine how to distribute data. Lots of different algorithms that can be used as consistent algorithms, as uniform distribution algorithms, but essentially it's that knowledge of what servers exist that drive the distribution of data. Of course, in Windows Azure, those servers that are running Memcached can come and go. So that client needs to be made aware of what's going on there. And you have to write code to do that. Finally, high availability, again, is something to bear in mind. If you're caching data to protect some back-end resource, and if you're reliable on that cache, if you're reliant on that cache being there, what happens when that cache goes away? You either need to cope with that or find a way of making the cache highly available. Windows Azure Cache, so we made this generally available this week as part of the 1.8 SDK. It knows about Windows Azure. You install it as part of either a tools or you run a PowerShell commandlet to install it into your app. The partitioning approach is server-driven. The servers in the cache are not standalone servers. They form a cluster. And the server tells the clients about the state of the ring. So the partitioning approach is driven by the server, not by the client. Finally, we have performance monitor counters in there, and we have some options for high availability. So the question to ask is, or the questions to ask is, what happens when either A, you do a rolling upgrade of your app, the guest OS gets updated, the host OS gets updated? Well, what we do with the Windows Azure cache is we actually move the data from nodes to node. And then we push that mapping back down to the client. So you get some degree of resiliency of your data in the cache whilst upgrades are happening. If you add or remove instances, what happens then? Well, if you add instances, we'll rebalance the cache and move data around. Unfortunately, if you remove instances, that doesn't happen. So you have to be quite careful about going from a large number of nodes in a cache and scaling down to a smaller number. You have to do it in stages. You can't go from 32 to 16. You'll see cascading failures. And then what happens if the nodes fail themselves? So one of the options we have in the Windows Azure cache is to make the cache highly available. And basically the way that works is that we create a secondary copy of the data. And when you write into the cache, we do a synchronous write to two nodes and then acknowledge back to the client. What this means is that you're protected now against node failure. If a computer crashes, if a top of rack switch fails in the rack that you're in, if the machine blue screens, if any sort of failure like that, you still have that data in the cache. Ultimately, what this means is that you can rely more, not entirely, rely more on your data being in the cache, which means that you can build applications that push the boundaries a little bit more in terms of that density idea. One thing to think about in terms of models for using the cache, and to some degree this is related to the classification of data that you put in the cache, but how do we get data in there? And there are typically three models for this. One is a very natural cache-aside model. It's used for session state, those sorts of things. The user logs in, needs a profile, goes to the cache, gets a cache miss, goes to the database, pushes the data into the cache, and from then on that data's there. Typically those things have a TTL associated with them and they expire out the cache. Other data, resource data, lookup data, those sorts of data, you might want to think about pushing that data into the cache, not having it done on demand, building something that basically enables the data to get from the backend store into the cache when it's needed, deals with things like expiration, when data becomes stale, what to do. What you don't want to do and what you're trying to optimize for here is to try to get the ratio of gets from the cache to puts into the cache as high as possible. You don't want a situation where the client detects data isn't missing in the cache, but you have 10,000 of them doing it at the same time, and they all race to the back end, hit the back end resource, and then it collapses under the pressure of the load. The final one, data pull, is a sort of a variation on the theme, and it's basically saying instead of running some daemon in the back end that's going to populate my cache for me, I'm going to have a service that I'm going to ask to populate the cache asynchronously. Typically this pattern is I detect some staleness in my data, I'm going to carry on serving that data, but I'm going to ask someone else to go refresh it for me. One of the challenges there is how do you work that out? And typically you end up with the problem around clock skew. So not all nodes in a distributed system have the same notion of time. And typically in Windows Azure that's very true. So you have to think carefully about whether the scenario that you have matches that sort of technique. So I managed to rush through that really quickly, and they've got 26 seconds left.
You, sir, are a genius.
A
temporal genius.
I must be just really lucky. So we talked about some of the scalability challenges around building stuff on Windows Azure. We talked a lot about partitioning applications, and we talked a little bit about optimizing state management. I can really recommend this paper at the bottom of the slide here, because Mark was one of the co-authors of it, and it makes it much easier for me to do it rather than you.
So,
We'll take questions in here now. We're here for the next session, so we're pretty much going to be here until about 6:15, I think.
they've got us here for quite some time. You can't see, but we're actually shackled back here.
So thank you very much for your time, and